Hello everyone. In this video we will talk about mathematical systems and groups. Alright, a mathematical system. When you're driving on city streets and you come to a four-way intersection, you have four choices: right, left, straight, or U-turn. What you don't realize is that you've just landed in the middle of a mathematical system. A mathematical system is a finite or infinite set of symbols and at least one operation. So if we were to talk about numbers, for example, we've talked about finite sets. For example, just the set 1, 2, 3, 4. That's a finite set with four things in it. An infinite set, something like the real numbers. So we wouldn't be able to list all of them out, but we can describe and talk about what that set is. So in this case, the example, the introduction here with four-way intersection, we're going to think about our four symbols as R, L, S, and U, which represent the four choices of turns that you could make at an intersection. All right, so we don't know what direction we're traveling in originally, but we'll kind of pick a direction. All right, and then we could look at the different turns. Okay, a right turn, of course, and then a left, and then going straight, right, or a U-turn. All right, so we need, to be a mathematical system, we need not only a set of symbols, but also an operation. So what is this operation? Well, think about what happens if you choose two of these turns in a row. Okay, so for example, if you go right and then left. All right, so if you turn right and then left, then you will end up going in the same direction you started in, whatever that was. All right, so this corresponds to going straight. So we can combine two of these turns and end up traveling in some direction, right? And that's our operation, combining two turns consecutively together. All right, so let's see, let's get a little illustration here. Okay, so here's your original direction of travel. All right, and if you turn right, you're going this way, and then you kind of have to turn your head to the side to see, but if you look in the direction of the arrow, right, then making a left turn if you're driving along this way, and then you turn left, you'd be going this direction. Right, now if you tilt your head back, facing the way that you were originally going, and you compare the two, okay, this one and this one, you can see that you're still traveling in the same direction. So we'll ignore the fact that it's now on a different street, but we would say that this is, you would be going in the same direction as if you had just continued straight to begin with. So for this example, right, a right turn plus a left turn ends up sending you straight. All right, how about a U-turn plus a left turn if we combine those two turns in a row? Okay, U-turn plus a left turn. All right, so here's your original direction, and then you make a U-turn, right, and then turn your head, upside down so that you're picturing driving along in this direction. Okay, then if you were to make a left turn, that's going to look like this, right? And then if you spin your head back so that you're facing the original direction and compare these two, you're now traveling in the same direction as if you had made just a single turn, as if you had just turned right to begin with. Okay, so a U-turn combined with a left turn sends you in that right direction. All right, so we can define that, that symbol, this plus symbol. Right, we don't have numbers anymore, so we have to decide what that symbol now represents. So we're going to use that to mean combining consecutive turns, and then we can look at all of these possible combinations. All right, so we already said that a right turn plus a left turn is the same as going straight. Right? Now when you read one of these operation tables, okay, this shows all the different combinations. So you list out all of your elements in the set, all right, R, L, S, and U, along the side and then across the top. Okay, and you make sure that the order matches. So if you start with right here, then you start with right up at the top. Okay, so now to find something like R plus L, all right, the ones down the side here are going to be the thing that comes first. Okay, and across the top would be the second element that's being combined. Okay, so R plus L, you would find R as the first one, plus L, and then you put the answer in the box where that row and column intersect. Okay, so right plus left, we said was straight. All right. Okay, let me clean this up. Okay, and then we said a U-turn plus a left turn sends you in the same direction as if you had just originally turned right. So U-turn plus left turn is right. Okay, now it would be a good idea to pause here, see if you can try some of these other ones. If not, then listen to the explanation of these. Okay, and then you could pause at any time, try this out, and see if you can figure it out. Okay, so a right, we'll kind of go in order here. A right turn plus a right turn is going to go here. Okay, so think about, here's your original direction, and make a right turn, then spin your head, make another right turn, and then you compare the original direction with the new direction. All right, and you want to pick R, L, S, or U, which direction are you traveling? Well, compared to the original, it's the same as if you had just made a U-turn to begin with. So right plus right is the same as a U-turn. Okay, right plus straight. Okay, original, right, straight is the same as if you had just turned right. All right, right plus U, here's your original, make a right turn, then make a U-turn, and that's the same as if you had originally turned left. Okay, left plus right. Now at this point in time, we don't know if this is, if this operation is commutative. It's not like normal addition. So I can't just assume that left plus right is the same thing as right plus left. So I still do have to think about what this would look like. Okay, so original, make a left turn, then make a right turn. Okay, compared to the original, you're going in the same direction. So that would be the same as if you had just continued straight to begin with. All right, left plus a left. Okay, original, left, left. Okay, that's the same as making a U-turn. Okay, left plus straight. So here's your original, kind of reuse here. Original, left, and then straight. Okay, so you're just going to continue in the same direction. So that's like just making a left turn. Left plus U. Original, left, U-turn sends you in the opposite direction. And compared to the original, that's the same as if you had turned right. Oops. Okay. Okay, straight plus right. Okay, original, straight, continue straight, okay, and then make a right turn. That's the same as a right turn. Straight plus left. Okay, so now original, straight, and left is left. Okay, straight plus straight. Original, straight, another straight, still going straight. Oops. Okay, straight plus a U-turn. Okay, original, straight, U-turn. And that's like making a U-turn. U-turn plus a right turn. Here's your original, U-turn, and then a right turn is the same as if you had just turned left. Okay, U-turn plus straight turn. Original direction, U-turn, continue straight is It's the same as if you made a U-turn. And finally, U-turn plus U-turn. Here's the original, U-turn, U-turn, and now you're going in the same direction as you were originally, so that is the same as going straight. Okay, so we have completed the operation table, and we now know what every possible combination of elements in this set is with this operation, this plus symbol. Okay, we'll come back to this. All right, one thing that we could do is find the answer to kind of like addition problems. All right, so some of these we can just look back at the chart. All right, like L plus S. All right, so you would go back and here's L, that's your first one. Here's S, and then you find the intersection, so L plus S is L. Okay, right plus right, U plus straight, okay, you can see those. Here's an example with 3 elements being added. All right, we do have kind of an order of operations here that apply, so we would do the parentheses first. Okay, so straight plus U is a U-turn. Okay, and then a U-turn plus a right turn, U plus R is L. All right. Okay, so this is a mathematical system. We have a set of elements, LRSU, and we have an operation plus. Now, one thing that we're interested in is what properties does this mathematical system have? So I already stated that we don't know yet whether or not it's commutative, but that's something that we would want to check. So there are 5 properties to check. Not all math systems have them. Your real number system does, right, but other systems don't. For instance, if you looked at matrix multiplication, you've probably seen this in algebra perhaps. All right, multiplying matrices, and you may have learned this, that this is not a commutative operation. Okay, so there are some systems that do have these, some that don't. All right, but let's test it out for our system composed of LRSU and this plus symbol. Okay, so let's back up. Here we go. Okay, closure. Right, so think back if you want to pause and maybe refresh yourself on the definitions of these properties. Based on, you can go back and look at how these worked with the real numbers, right? And closure property said what? Okay, closure property says that when you combine 2 real numbers, and we talked about either addition or multiplication, right? When you combine 2 real numbers, you get a real number as an answer. So for this system, we're just checking when we combine different elements, okay, from RL, S, and U with different elements. Right? Do we always get one of those elements? Does it stay in that set, RLSU, or does it ever leave the set and have a different answer? Well, an easy way to check, you just look at the kind of the inside of your table here, and you just look and make sure that everything is an R, an L, an S, or a U. Okay, so this does have the closure property. Okay, so closure, yes. All right, the next one is commutative. Is it commutative? Okay, so we could check a couple. For instance, R plus L, and remember the commutative property says that we can reverse the order in which these are added, and hopefully we get the same answer. All right, so let's check. R plus L is here, and L plus R is here. Okay, and those match. Right, now that just checks it in one case. We would have to check every single other combination. So fortunately this is a small system, so it's not too hard to do. All right, now notice the ones on the diagonal like R plus R. We don't really need to check R plus R because when you switch the order you're not going to even be able to tell. So we really don't look at these guys, okay, R plus R, L plus L, etc. We're interested in the ones where we're combining 2 different elements. Okay, so we'll check some of those. All right, S plus R. Let's see if that's the same as R plus S. Oops. All right, so S plus R is here, and R plus S is here, and those are both R, so those are equal. All right, now you might notice if you look at the placement here, there's a quick way to do this to check these are actually reflections of each other across that diagonal, right? And I could draw in some other ones, like here, there's another set. Okay, these guys, this is u plus r and r plus u. Here's u plus l plus u, right? So if you kind of think of drawing like little lines across that diagonal, you're just checking, does everything match? If you fold along this diagonal line, would everything line up? And if so, then that's so the system does have the commutative property. All right, so this one is commutative. Oops, uh-oh. Okay, I actually want to back up here. Okay, I'm going to pause and rewrite this, and I'll come back in just a second. Okay, so I've recopied that a little more neatly. All right, let's check the next property, the identity property. Okay, so think about with addition of real numbers. What is the identity property? Oops. All right, and this one says if you have a real number, we'll just call it x, okay, that there is another special number that you can add to that that doesn't change the value of x, right? And that number is called 0, so 0 is the identity for addition. Okay, we could say that it's the identity element. Right, it's something in the set of real numbers that doesn't change the value of other real numbers when it's added to it. Okay, so example, 15 plus 0 equals 15. Right, and notice also 0 plus 15 is 15. And we know that because of the commutative property, but if you had a system that wasn't commutative, then you would still want to check and make sure that that's a true fact. All right, so let's think about our system. If we're looking for an identity, okay, if we're looking for an identity, then we are looking for some element in the set, LRSU, that could be added to all the other elements without changing it. So for instance, L plus something should equal L, R plus something should equal R, S plus something equals S, and U plus something should still equal U. Right? Now just like with 0, we want it to be the same number that works for all 4 of these equations. All right, we're looking for one identity element. All right, so if you've caught on to this, and if you've already figured this out, okay, you can look from the chart here. And, okay, I would go to the L column, for example, and I want to see L plus what equals L. Well, follow it all across to where you have an answer of L, then follow it up and see what was added to it. So it looks like L plus S was what equaled L. L plus S equals L. Right, now if S is the identity, then this should hopefully be true for all of these. All right, so let's go back and look. All right, so we'll find the S column. Okay, here's R plus S is R, L plus S is L, S plus S is S, and U plus S is U. Okay, and that works. Now a quick way to check this, just read down, right, RLSU, and if you have a column that matches that RLSU, then that entire column has been unchanged by whatever was added, in this case the S. Right. Now we also have to check the other direction, particularly if we didn't know that this was commutative. We want to say what plus L equals L, okay, what plus R equals R, and so forth. All right, so now I would go back, and I don't know what the first number is, okay, but I want to check all of these second numbers and see if there's something that I can add to those that leaves it unchanged. All right, so I would follow, for example, R down, look for the answer of R, and see what was added to R to leave it as an R. So what plus R equals R. And you can see from here, that's S again. And we do want to see that. Hopefully we see the same thing. All right, now if you follow it across, here's S plus L, S plus S, and S plus U. And all of them, RLSU matches RLSU, right? So that shows that there is an identity. Okay, and this can be filled in with S. All right, so then we say that yes, the system does have the identity property. Oops, where is it? Okay, we have closure, it is commutative, it does have the identity property, and we say S is the identity. Okay, and we have two more to check, inverse and associative. Okay, so let's do inverse next. This one fits nicely with identity. So think about what this means for real numbers when we talked about addition, and let's say we talk about the inverse of 5. All right, well then we're asking 5 plus what, and then our test here, if numbers are inverses, then they should add up to be 0. Okay, so 5 plus what is 0, and the answer is -5. Right, or if you look at maybe a fraction, 3/4 plus what is 0. Okay, and the answer is -3/4. So it turns out that for real numbers, the inverse is always just the opposite, just put a negative sign with it. Right, well, for our system, we want to do kind of the same thing, but we're testing a slightly different equation here because we don't have a 0, but instead we do have an identity. So what we're looking for is we have some element, and we can fill that in with like an L or an R, etc. And we want to add something to it, we don't know what yet, and hopefully we get the identity, call it ID, which in this case we've said for this system, that's a straight term. Right? Straight term is what you can combine with any of the other terms without changing that term. Okay, so if we tested it out, let's say we want to find the inverse of a left turn. Well, then we want to know what kind of undoes a left turn, left plus what, would send you in a straight direction. Okay, and you can just think about that in terms of streets, or you can go back to your chart. L plus what is S. Okay, so here's your L. Follow it across to where you see an answer of S and see what you had to add to it to get a straight. And it looks like it's a right turn. Okay, for a right turn, right plus what is straight. Okay, so find R, then follow it across until you see an answer of straight, and then see what you had to add to it. And it's a left turn. Right, so right and left turns are inverses of each other. Now straight turn, straight plus what is straight. Okay, so here's straight, followed across, find an answer of straight, and straight was added to itself to get another straight turn. Okay, and then finally U plus what is S. Here's U, followed across, find S. U plus U equals S. So it turns out that a straight turn and a U-turn, a straight turn is its own inverse. A U-turn is its own inverse. Right? And if you think about this in terms of straight directions, okay, let's say you're traveling and then you go straight and then you go straight, you've never changed your direction of travel. And for U-turns, here's your original, then you make a U-turn, and then you make another U-turn, so those two U-turns undo each other, and you end up just still traveling in your original direction. Okay, so this system does have the inverse property, and then we could go through and find the inverse for each of those elements. Okay? Associative property. This is the last one. This is hard to check for an entire system. There are just too many options. It's not too bad when you have a finite system, something like this with only 4 elements, but even so it would take a while to check the associative property. So what we do is we just check a few examples, and then we kind of get a feel for whether or not we think this would be true all the time. And it is more of a conjecture. We don't know for sure, but thankfully systems in a lot of cases are fairly well behaved, and that means that if you try a few examples, then that pattern does seem to kind of hold. Okay, so let's check this. Remember, for real numbers, okay, the associative property says that adding 2 numbers first and then adding a third is the same as if you regroup this and add the second 2 numbers first. All right, so for our system, we could check something like left plus right plus u. And then we want to see, is that the same thing as a left turn plus whatever we get if we've already combined a right turn plus a U-turn. Okay, so you're changing the parentheses, but not the order of the elements. Okay, so from your table, okay, check L plus R plus U. Okay, so left plus right is a straight, and straight plus U is a U-turn. Okay, and then check L plus R plus U. Okay, so R plus U first is a left turn, and then left plus left is a U. Okay, and those match, those are equal. So at this point you might make a guess or a conjecture that this is associative. You could try a couple other examples if you wanted to see for sure. Or not for sure, but you know, make a better guess or be a little more confident of your answer. So you'll just have to trust us on this one. This system is associative. That property does hold. Right? I would probably never ask you to prove this, but rather just try a couple examples and then make a conjecture. All right, easy ways to check if a system has these properties. All right, so a quick review. We talked about closure. Here's another example. A finite system made up of the numbers 0, 1, 2, 3, 4, and then normal addition. Okay, as you know it. Okay, so closure first of all. When we add numbers in this set, do we always get an answer that's in that set? Well, looking at the table, if you just pick out and look, you can see, you know, here are a bunch of answers that are not in that set. Actually, here are all of them. So this is not closed. All right, it's normal addition, but because we've restricted it to just some of these numbers, then it's, you know, has some different properties. Okay, so not closed. Commutative. Right, here's your diagonal, and you want to look on either side and see if changing the order of addition makes a difference. Right, now this is normal addition, and we know that that's commutative, so we can feel good about this, but you can use this check as well for other systems that you're not familiar with. And all of those numbers match, so this is a commutative system. Okay, identity. All right, so the quick way, 0, 1, 2, 3, 4 in this order, you want to look across and see if there's another column that matches. And here's one. Okay, and then, all right, the row, 0, 1, 2, 3, 4, here's one that matches. And then just kind of follow that back and see what number it is that was added that left everything unchanged. Okay, and that's a 0. So your identity property does hold, yes, and then the identity is 0. And that's as expected. This is just normal addition. Inverse properties. Okay, well, notice what we did for the ones before. We had to look for that identity property as an answer and then see what we had to add to it to get the identity. So here, if I wanted to find, for example, the inverse of 3, then I'm asking 3 plus what equals 0? All right, so I would scan that row and look for a 0, and there is no 0. I don't see one in there. So that means that 3 does not have an inverse in this system. Now, certainly we know that 3 plus negative 3 is 0, but the problem is that negative 3 is not in this system. We don't see it in this table. So that's what we're looking for. So a quick check, you would just scan every row and column and make sure that you see the identity. All right, so here it is, but we only see it in one spot. It's not in any of these rows, and it's not in any of these columns. So in this system, 0 is the only thing that has an inverse. Okay, but that's not enough to say that the property holds for the whole system. So no, that does not hold. Associative. Okay, you could try a couple of these, and you will see that it is associative. And we know that that's true because it's normal addition. All right. One more example. This one has really no real-life context, but you're just given this system, and here's your set of elements, 0, 1, 2, 3, and you're given this operation, an and sign. All right, I'll draw mine like that. So we don't know what this is. It's definitely not addition, probably doesn't follow the normal rules of any of our operations, but we just want to think of it as a way of combining two of these elements or pairing them up. Okay, so 0 and 1 or 0 and 3. All right, so we'll check these properties and we can just do the shortcut this way. All right, so closure. Look through the answers in your table and see if you always get a 0, 1, 2, or 3, or if you get anything else. Right, in this one, they're all in the set, so that is a closed system. Okay, associative. All right, well, let's try one example. All right, how about, let's see, 2 plus 3 plus 1. Okay, and then we'll try 2 plus, in parentheses, 3 plus 1 and see if they match. Okay. Oh, and actually I'm saying plus, but I really shouldn't be saying that. It's an and sign here. It's not really a plus. Okay. So 2 and 3. It's not 5. Okay? We're going to follow the table, not your normal rules for addition. Okay, so here's 2, here's 3, and 2 and 3 is actually a 3. Right? 3 and 1. 3 and 1 is 0. Okay, so it's kind of weird. It's more of an abstract idea, but you're just reading off what's written in the table. All right, 3 and 1. Okay, 3 and 1 is 0. And 2 and 0, 2 and 0 makes 0. Right, so at least in this case, these match, and then if you wanted to make a conjecture at this point, yeah, we're going to make a conjecture that this is an associative system. And if I remember correctly, I think this one does turn out to be associative. Okay, identity. All right, identity. So we're looking for something that leaves 0, 1, 2, 3 unchanged, so quickly scan, look for another column that matches. Here it is. Okay, so 2, that looks like a good candidate for the identity. So let's make sure and check the row as well. 0, 1, 2, 3. Great. Okay, so yes, this has the identity, and the identity is 2. Okay. Inverses. If the system has the inverse property, then we should always be able to add something to each of these numbers to get 2 as an answer. All right, so I would scan rows and columns and make sure each one has a 2, and they do, so yes, the inverse property holds. All right. Now we could phrase the question differently. We could say, for example, what is the inverse of 3? And now we're asking, what do we add to 3 to get the identity, which we said was 2? All right, so I would scan across. Here's 3. Here's an answer of 2. Follow it up. Looks like I added 3. So the inverse of 3 is 3. All right, inverse of 2 is 2. Inverse of 1 is 1. Okay, 0 and 0 makes 2. So 0 is the inverse of 0. So every element is actually its own inverse. Kind of weird. Okay, we will pause there, and I will see you in the next video.